Section 6 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain. Recorded by Leon Harvey. Chapter 6. The Climatic Stress of the 14th Century. In order to give concreteness to our picture of the climatic pulsations of historic times, let us take a specific period and see how its changes of climate were distributed over the globe, and how they are related to the little changes which now take place in the sunspot cycle. We will take the 14th century of the Christian era, especially the first half. This period is chosen because it is the last and hence the best known of the times when the climate of the earth seems to have taken a considerable swing toward the conditions which now prevail when the sun is most active, and which, if intensified, would apparently lead to glaciation. It has already been discussed in World Power and Evolution, but its importance and the fact that new evidence is constantly coming to light warrant a fuller discussion. To begin with Europe, according to the careful account of Patterson, the 14th century shows a record of extreme climatic variations. In the cold winters, the rivers Rhine, Danube, Thames, and Po were frozen for weeks and months. On these cold winters there followed violent floods, so that the rivers mentioned inundated their valleys. Such floods are recorded in 55 summers in the 14th century. There is, of course, nothing astonishing in the fact that the inundations of the great rivers of Europe were more devastating 600 to 700 years ago than in our days, when the flow of the rivers has been regulated by canals, locks, etc. But still the inundations in the 13th and 14th centuries must have surpassed everything of that kind which has occurred since then. In 1342 the waters of the Rhine rose so high that they inundated the city of Mainz and the cathedral Asque ad Cinculum Hominis. The walls of Cologne were flooded so that they could be passed by boats in July. This occurred also in 1374 in the midst of the month of February, which is of course an unusual season for disasters of the kind. Again in other years the drought was so intense that the same rivers, the Danube, Rhine, and others, nearly dried up, and the Rhine could be forded at Cologne. This happened at least twice in the same century. There is one exceptional summer of such evil recorded that centuries afterwards it was spoken of as the old hot summer of 1357. Patterson goes on to speak of two oceanic phenomena on which the old chronicles lay greater stress than all the others. The first is the great storm floods on the coast of the North Sea and the Baltic, which occurred so frequently that not less than 19 floods of a destructiveness unparalleled in later times are recorded from the 14th century. The coastline of the North Sea was completely altered by these floods. Thus on January 16, 1300, half the island Heligoland and many other islands were engulfed by the sea. The same fate overtook the island of Borkum, torn to several islands by the storm flood of January 16, which remoulded the Frisian islands into their present shape. When also Windingstadt, on the island of Sylt, and Thiriu parishes were engulfed. This flood is known under the name of the Great Man Drowning. The coasts of the Baltic also were exposed to storm floods of unparalleled violence. On November 1st, 1304, the island of Rügen was torn asunder from Rügen by the force of the waves. Time does not allow me to dwell upon individual disasters of this kind, but it will be well to note that of the 19 great floods on record, 18 occurred in the cold season between the autumnal and vernal equinoxes. The second remarkable phenomenon mentioned by the chronicles is the freezing of the entire Baltic, which occurred many times during the cold winters of these centuries. On such occasions it was possible to travel with carriages over the ice from Sweden to Bornholm, and from Denmark to the German coast, Lübeck, and in some cases even from Gotland to the coast of Estland. Norland says that the only authentic accounts of the complete freezing of the Baltic in the neighbourhood of the Kattegat are in the years 1296, 1306, 1323, and 1408. Of these, 1296 is much the most uncertain, while 1323 was the coldest year ever recorded, as appears from that fact that horses and sleighs crossed regularly from Sweden to Germany on the ice. Not only Central Europe and the shores of the North Sea were marked by climatic stress during the 14th century, but Scandinavia also suffered. As Patterson puts it, On examining the historic data from the last centuries in the Middle Ages, Dr. Bull of Christiania has come to the conclusion that the decay of the Norwegian kingdom was not so much a consequence of the political conditions at that time, as of the frequent failures of the harvest, so that corn, wheat for bread had to be imported from Lübeck, Rostock, Wismar, and so forth. The Hansa Union undertook the importation and obtained political power by its economic influence. The Norwegian landowners were forced to lower their rents. The population decreased and became impoverished. The revenue sank 60 to 70%. Even the income from church property decreased. In 1367, corn was imported from Lübeck to a value of 500,000 kroner. The trade balance inclined to the disadvantage of Norway, whose sole article of export at that time was dried fish. The production of fish increased enormously in the Baltic regions of South Sweden because of the same changes which were influencing the lands, but this did not benefit Norway. Dr. Bull draws a comparison with the conditions described in the sagas when Nordland, at the Arctic Circle, produced enough corn to feed the inhabitants of the country. At the time of Asbjorn Selsbane, the chieftains in Trondhenes, still farther north in latitude 69 degrees, grew so much corn that they did not need to go southward to buy corn unless 3 successive years of dearth had occurred. The province of Trondheim exported wheat to Iceland and so forth. Probably the turbulent political state of Scandinavia at the end of the Middle Ages was in a great measure due to unfavorable climatic conditions, which lowered the standard of life, and not entirely to misgovernment and political strife, as has hitherto been taken for granted. During this same unfortunate first half of the 14th century, England also suffered from conditions which, if sufficiently intensified, might be those of a glacial period. According to Thorwald Rogers, the severest famine ever experienced in England was that of 1315 to 1316, and the next worst was in 1321. In fact, from 1308 to 1322, great scarcity of food prevailed most of the time. Other famines of less severity occurred in 1351 and 1369. The same cause was at work in all these cases, says Rogers. Incessant rain and cold, stormy summers. It is said that the inclemency of the seasons affected the cattle, and that numbers perished from disease and want. After the bad harvest of 1315, the price of wheat, which was already high, rose rapidly, and in May 1316 was about 5 times the average. For a year or more thereafter it remained at 3 or 4 times the ordinary level. The severity of the famine may be judged from the fact that previous to the Great War, the most notable scarcity of wheat in modern England, and the highest relative price was in December 1800. At that time wheat cost nearly 3 times the usual amount, instead of 5 as in 1316. During the famine of the early 14th century, it is said that people were reduced to subsist upon roots, upon horses and dogs, and stories are told of even more terrible acts by reason of the extreme famine. The number of deaths was so great that the price of labour suffered a permanent rise of at least 10%. There simply were not people enough left among the peasants to do the work demanded by the more prosperous class who had not suffered it so much. After the famine came drought. The year 1325 appears to have been peculiarly dry, and 1331, 1344, 1362, and 1377 were also dry. In general, these conditions do little harm in England. They are of interest chiefly as showing how excessive rain and drought are apt to succeed one another. These facts regarding northern and central Europe during the 14th century are particularly significant when compared with the conclusions which we have drawn in Earth and Sun from the growth of trees in Germany and from the distribution of storms. A careful study of all the facts shows that we are dealing with 2 distinct types of phenomena. In the first place, the climate of Central Europe seems to have been peculiarly continental during the 14th century. The winters were so cold that the rivers froze, and the summers were so wet that there were floods every other year or oftener. This seems to be merely an intensification of the conditions which prevail at the present time during periods of many sunspots, as indicated by the growth of trees at Eberswald in Germany, and by the number of storms in winter as compared with summer. The prevalence of droughts, especially in the spring, is also not inconsistent with the existence of floods at other seasons. For one of the chief characteristics of a continental climate is that the variations from one season to another are more marked than in oceanic climates. Even the summer droughts are typically continental, for when continental conditions prevail, the difference between the same region in different years is extreme, as is well illustrated in Kansas. It must always be remembered that what causes famine is not so much absolute dryness as a temporary diminution of the rainfall. The second type of phenomena is peculiarly oceanic in character. It consists of two parts, both of which are precisely what would be expected if a highly continental climate prevailed over the land. In the first place, at certain times, the cold area of high pressure, which is a predominating characteristic of a continent during the winter, apparently spread out over the neighboring oceans. Under such conditions, an inland sea, such as the Baltic, would be frozen, so that horses could cross the ice even in the far west. In the second place, because of the unusually high pressure over the continent, the barometric gradients apparently became intensified. Hence, at the margin of the continental high-pressure area, the winds were unusually strong and the storms' corresponding severity. Some of the storms may have passed entirely along oceanic tracks, while others invaded the borders of the land and gave rise to the floods and to the wearing away of the coast described by Peterson. Turning now to the east of Europe, Bruckner's study of the Caspian Sea shows that that region, as well as Western Europe, was subject to great climatic vicissitudes in the first half of the 14th century. In 1306 to 1307, the Caspian Sea, after rising rapidly for several years, stood 37 feet above the present level, and it probably rose still higher during the succeeding decades. At least it remained at a high level, for Hamdullah, the Persian, tells us that in 1325 a place called Aboskan was underwater. Still further east of the inland lake of Lop Nor also rose at about this time. According to a Chinese account, the Dragon Tower on the shore of Lop Nor was destroyed by a flood. From Himley's translation, it appears that the level of the lake rose so as to overwhelm the city completely. This would necessitate the expansion of the lake to a point 80 miles east of Lulan, and fully 50 from the present eastern end of the Karakoshan Marsh. The water would have to rise nearly or quite to a strand which is now clearly visible at a height of 12 feet above the modern lake or marsh. In India, the 14th century was characterized by what appeared to have been the most disastrous drought in all history. Apparently the decrease in rainfall here was as striking as the increase in other parts of the world. No statistics are available, but we are told that in the Great Famine which began in 1344, even the Mughal emperor was unable to obtain the necessaries of life for his household. No rain worth mentioning fell for years. In some places the famine lasted 3 or 4 years, and in some 12, and entire cities were left without an inhabitant. In a later famine, 1769 to 1770, which occurred in Bengal shortly after the foundation of British rule in India, but while the native officials were still in power, a third of the population, or 10 out of 30 millions, perished. The famine in the first half of the 14th century seems to have been far worse. These Indian famines were apparently due to weak summer monsoons, caused presumably by the failure of Central Asia to warm up as much as usual. The heavier snowfall and the greater cloudiness of the summer there, which probably accompanied increased storminess, may have been the reason. The New World, as well as the Old, appears to have been in a state of climatic stress during the first half of the 14th century. According to Peterson, Greenland furnishes an example of this. At first the inhabitants of that Northland were fairly prosperous and were able to approach from Iceland without much hindrance from the ice. Today the North Atlantic Ocean, northeast of Iceland, is full of drift ice much of the time. The border of the ice varies from season to season, but in general it extends westward from Iceland, not far from the Arctic Circle, and then follows the coast of Greenland southward to Cape Farewell at the southern tip and around the western side for 50 miles or more. Except under exceptional circumstances, a ship cannot approach the coast until well northward, on the comparatively ice-free west coast. In the old sagas, however, nothing is said of ice in this region. The route from Iceland to Greenland is carefully described. In the earliest times, it went from Iceland to travel north or west, so as to approach the coast of Greenland after as short an ocean passage as possible. Then it went down the coast in a region where approach is now practically impossible because of the ice. At that time, this coast was icy close to the shore, but there is no sign that navigation was rendered difficult, as is now the case. Today, no navigator would think of keeping close inland. The old route also west-north of the island on which Cape Farewell is located, although the narrow channel between the island and the mainland is now so blocked with ice that no modern vessel has ever penetrated it. By the 13th century, however, there appears to have been a change. In the Kugelspergel, or King's Mirror, written at that time, navigators are warned not to make the east coast too soon on account of ice. But no new route is recommended in the neighbourhood of Cape Farewell or elsewhere. Finally, however, at the end of the 14th century, nearly 150 years after the Kungelsbergel, the old sailing route was abandoned, and ships from Iceland sailed directly southward to avoid the ice. As Peterson says, at the end of the 13th and the beginning of the 14th century, the European civilization in Greenland was wiped out by an invasion of the Aboriginal population. The colonists in the Vestibioid were driven from their homes and probably migrated to America, leaving behind their cattle in the fields. So they were found by Ivar Bardason, steward to the Bishop of Gardar, in his official journey thither in 1342. The Eskimo invasion must not be regarded as a common raid. It was a transmigration of a people, and like other big movements of this kind, was impelled by altered conditions of nature. In this case, the alterations of climate caused by, or which caused, the advance of the ice. For their hunting and fishing, the Eskimos required an at least partially open Arctic Sea. The seal, their principal prey, cannot live where the surface of the sea is entirely frozen over. The cause of the favourable conditions in the Viking Age was, according to my hypothesis, that the ice then melted at a higher latitude in the Arctic seas. The Eskimos then lived further north in Greenland and North America. When the climate deteriorated and the sea which gave them their living was closed by ice, the Eskimos had to find a more suitable neighbourhood. This they found at land colonized by the Norsemen, whom they attacked and finally annihilated. Finally, far to the north in Yucatan, the ancient Maya civilization made its last flickering effort at about this time. Not much is known of this, but in earlier periods the history of the Mayas seems to have agreed quite closely with the fluctuations in climate. Among the Mayas, as we have seen, relatively dry periods were the times of greatest progress. Let us now turn to Figure 3 once more, and compare the climatic conditions of the 14th century with those of periods of increasing rainfall. Southern England, Ireland, and Scandinavia, where the crops were ruined by extensive rain and storms in summer, are places where storminess and rainfall now increase when sunspots are numerous. Central Europe and the coast of the North Sea, where floods and drought alternated, are regions which now have relatively less rain when sunspots increase than when they diminish. However, as appears from the trees measured by Douglas, the winters become more continental and hence cooler, thus corresponding to the cold winters of the 14th century when people walked on the ice from Scandinavia to Denmark. When such high pressure prevails in the winter, the total rainfall is diminished, but nevertheless the storms are more severe than usual, especially in the spring. In southeastern Europe, the part of the area whence the Caspian derives its water appears to have less rainfall during times of increasing sunspots than when sunspots are few. But in an equally large area to the south, where the mountains are higher and the runoff of the rain is more rapid, the reverse is the case. This seems to mean that a slight diminution in the water poured in by the Volga would be more than compensated by the water derived from Persia and from the Oxus and Jaxartes rivers, which in the 14th century appear to have filled the Sea of Aral and overflowed in a large stream to the Caspian. Still farther east in Central Asia, so far as the records go, most of the country receives more rain when sunspots are many than when they are few, which would agree with what happened when the Dragon Tower was inundated. In India, on the contrary, there is a large area where the rainfall diminishes at times of many sunspots. thus agreeing with the terrible famine from which the Mongols suffered so severely. In the Western Hemispheres, Greenland, Arizona, and California are all parts of the area where the rain increases with many sunspots, while Yucatan seems to lie in an area of the opposite type. Thus, all the evidences seem to show that at times of climatic stress, such as the 14th century, the conditions are essentially the same as those which now prevail at times of increasing sunspots. As to the number of sunspots, there is little evidence previous to about 1750. Yet that little is both interesting and important. Although sunspots have been observed with care in Europe only little more than 3 centuries, the Chinese have records which go back nearly to the beginning of the Christian era. Of course, the records are far from perfect, for the work was done by individuals and not by any great organization which continued the same methods from generation to generation. The mere fact that a good observer happened to use his smoked glass to advantage may cause a particular period to appear to have an unusual number of spots. On the other hand, the fact that such an observer finds spots at some times and not at others tends to give a valuable check on his results, as does a comparison of one observer's work with that of another. Hence, in spite of many and obvious defects, most students of the problem agree that the Chinese record possesses much value, and that, for 1,000 years or more, it gives a fairly true idea of the general aspect of the sun. In the Chinese records, the years with many spots fall in groups, as would be expected, and are sometimes separated by long intervals. Certain centuries appear to have been marked by unusual spottedness. The most conspicuous of these is the 14th, when the years 1370 to 1385 were particularly noteworthy, for spots large enough to be visible to the naked eye covered the sun much of the time. Hence Wolf, who has made an exhaustive study of the matter, concludes that there was an absolute maximum of spots at about 1372. While this data is avowedly open to question, the great abundance of sunspots at that time makes it probable that it cannot be far wrong. If this is so, it seems that the great climatic disturbances of which we have seen evidence in the 14th century occurred at a time when sunspots were increasing, or at least when solar activity was under some profoundly disturbing influence. Thus the evidence seems to show not merely that the climate of historic times has been subject to important pulsations, but that those pulsations were magnifications of little climatic changes which now take place in sunspot cycles. The past and present are apparently a unit except as to the intensity of the changes. End of section 6. Chapter 7. Glaciation according to the solar cyclonic hypothesis. The remarkable phenomena of glacial periods affords perhaps the best available test to which any climatic hypothesis can be subjected. In this chapter and the 2 that follow, we shall apply this test. Since much more is known about the recent Great Ice Age, or the Pleistocene glaciation, than about the more ancient glaciations, the problems of the Pleistocene will receive especial attention. In the present chapter, the oncoming of glaciation and the subsequent disappearance of the ice will be outlined in the light of what would be expected according to the solar cyclonic hypothesis. Then in the next chapter, several problems of especial climatic significance will be considered, such as the localization of ice sheets, the succession of severe glacial and mild interglacial epochs, the sudden commencement of glaciation, and the peculiar variations in the height of the snowline. Other topics to be considered are the occurrence of pluvial or rainy climates in non-glaciated regions, and glaciation near sea level in subtropical latitudes during the Permian and Proterozoic. Then in Chapter 9 we shall consider the development and distribution of the remarkable deposits of wind-blown material known as loess. Facts not considered at the time of framing an hypothesis are especially significant in testing it. In this particular case, the cyclonic hypothesis was framed to explain the historic changes of climate revealed by a study of ruins, tree rings, and the terraces of streams and lakes, without special thought of glaciation or other geologic changes. Indeed, the hypothesis had reached nearly its present form before much attention was given to geological phases of the problem. Nevertheless, it appears to meet even this severe test. According to the solar cyclonic hypothesis, the Pleistocene glacial period was inaugurated at a time when certain terrestrial conditions tended to make the Earth especially favorable for glaciation. How these conditions arose will be considered later. Here it is enough to state what they were. Chief among them was the fact that the continents stood unusually high and were unusually large. This, however, was not the primary cause of glaciation, for many of the areas which were soon to be glaciated were little above sea level. For example, it seems clear that New England stood less than 1,000 feet higher than now. Indeed, Salisbury estimates that eastern North America in general stood not less than a few hundred feet higher than now, and W.B. Bright reaches the same conclusion in respect to the British Isles. Nevertheless, widespread lands, even if they are not all high, lead to climatic conditions which favor glaciation. For example, enlarged continents cause low temperatures in high latitudes because they interfere with the ocean currents that carry heat polewards. Such conditions also cause relatively cold winters, for lands cool much sooner than does the ocean. Another result is a diminution of water vapor, not only because cold air cannot hold much vapor, but also because the oceanic area from which evaporation takes place is reduced by the emergence of the continents. Again, when the continents are extensive, the amount of carbonic acid gas in the atmosphere probably decreases, for the augmented erosion due to uplift exposes much igneous rock to the air, and weathering consumes the atmospheric carbon dioxide. When the supply of water vapor and of atmospheric carbon dioxide is small, an extreme type of climate usually prevails. The combined result of all these conditions is that continental emergence causes the climate to be somewhat cool and to be marked by relatively great contrast from season to season and from latitude to latitude. When the terrestrial conditions thus permitted glaciation, unusual solar activity is supposed to have greatly increased the number and severity of storms, and to have altered their location, just as now happens at times of many sunspots. If such changes in storminess had occurred when terrestrial conditions were unfavorable for glaciation, as for example, when the lands were low and there were widespread epicontinental seas in middle and high latitudes, glaciation might not have resulted. In the Pleistocene, however, terrestrial conditions permitted glaciation, and therefore the supposed increase in storminess caused great ice sheets. The conditions which prevail at times of increased storminess have been discussed in detail in Earth and Sun. Those which apparently brought on glaciations seem to have acted as follows. In the first place, the storminess lowered the temperature of the Earth's surface in several ways. The most important of these was a rapid upward convection in the centers of cyclonic storms, whereby abundant heat was carried to high levels, where most of it was radiated away into space. The marked increase in the number of tropical cyclones, which accompanies increased solar activity, was probably important in this respect. Such cyclones carry vast quantities of heat and moisture out of the tropics. The moisture, to be sure, liberates heat upon condensing, but as condensation occurs above the Earth's surface, much of the heat escapes into space. Another reason for low temperature was that under the influence of the supposedly numerous storms of Pleistocene times, evaporation over the oceans must have increased. This is largely because the velocity of the winds is relatively great when storms are strong, and such winds are powerful agents of evaporation. But evaporation requires heat, and hence the strong winds lower the temperature. The second great condition which enabled increased storminess to bring on glaciation was the location of the storm tracks. Collimer's maps, as illustrated in Figure 2, suggest that a great increase in solar activity, such as is postulated in the Pleistocene, might shift the main storm track poleward, even more than it is shifted by the milder solar changes during the 12-year sunspot cycle. If this is so, the main track would tend to cross North America through the middle of Canada instead of near the southern border. Thus there would be an increase in precipitation in about the latitude of the Guyotine and Labradorian centers of glaciation. From what is known of storm tracks in Europe, the main increase in the intensity of storms would probably center in Scandinavia. Figure 3 in Chapter 5 bears this out. That figure, it will be recalled, shows what happens to precipitation when solar activity is increasing. A high rate of precipitation is especially marked in the boreal storm track, that is, in the northern United States, southern Canada, and northwestern Europe. Another important condition in bringing on glaciation would be the fact that when storms are numerous, the total precipitation appears to increase in spite of the slightly lower temperature. This is largely because of the greater evaporation. The excessive evaporation arises partially from the rapidity of the winds, as already stated, and partially from the fact that in areas where the air is clear, the sun would presumably be able to act more efficiently than now. It would do so because at times of abundant sunspots, the sun in our own day has a higher solar constant than at times of milder activity. Our whole hypothesis is based on the supposition that what now happens at times of many sunspots was intensified in glacial periods. A fourth condition which would cause glaciation to result from great solar activity would be the fact that the portion of the yearly precipitation falling as snow would increase, while the proportion of rain would diminish in the main storm track. This would arise partially because the storms would be located farther north than now, and partially because of the diminution in temperature due to the increased convection. The snow in itself would still further lower the temperature, for snow is an excellent reflector of sunlight. The increased cloudiness which would accompany the more abundant storms would also cause an unusually great reflection of the sunlight and still further lower the temperature. Thus, at times of many sunspots, a strong tendency toward the accumulation of snow would arise from the rapid convection and consequent low temperature, from the northern location of storms, from the increased evaporation and precipitation, from the larger percentage of snowy rather than rainy precipitation, and from the great loss of heat due to reflection from clouds and snow. If events at the beginning of the last glacial period took place in accordance with the cyclonic hypothesis, as outlined above, one of the inevitable results would be the production of snowfields. The places where snow would accumulate in special quantities would be central Canada, the Labrador Plateau, and Scandinavia, as well as in certain mountain regions. As soon as a snowfield became somewhat extensive, it would begin to produce striking climatic alterations in addition to those to which it owed its origin. For example, within a snowfield, the summers remain relatively cold, hence such a field is likely to be an area of high pressure at all seasons. The fact that the snowfield is always a place of relatively high pressure results in outblowing surface winds except when these are temporarily overcome by the passage of strong cyclonic storms. The storms, however, tend to be concentrated near the margins of the ice throughout the year instead of following different paths in each of the 4 seasons. This is partially because cyclonic lows always avoid places of high pressure and are thus pushed out of the areas where permanent snow has accumulated. On the other hand, at times of many sunspots, as Coleman has shown, the main storm track tends to be drawn poleward, perhaps by electrical conditions. Hence, when a snowfield is present in the north, the lows, instead of migrating much farther north in summer than in winter as they now do, would merely crowd on the snowfield a little farther in summer than in winter. Thus, the heavy precipitation which is usual in humid climates near the centers of lows would take place near the advancing margin of the snowfield and cause the field to expand still further southward. The tendency toward the accumulation of snow on the margins of the snowfields would be intensified not only by the actual storms themselves, but by other conditions. For example, the coldness of the snow would tend to cause prompt condensation of the moisture brought by the winds that blow toward the storm centers from low latitudes. Again, in spite of the general dryness of the air over a snowfield, the lower air contains some moisture due to evaporation from the snow by day during the clear sunny weather of anticyclones or highs. Where this is sufficient, the cold surface of the snowfields tend to produce a frozen fog whenever the snowfield is cooled by radiation, as happens at night and during the passage of highs. Such a frozen fog is an effective reflector of solar radiation. Moreover, because ice has only half the specific heat of water and is much more transparent to heat, such a radiation fog, composed of ice crystals, is a much less effective retainer of heat than clouds or fog made of unfrozen water particles. Shallow fogs of this type are described by several polar expeditions. They clearly retard the melting of the snow and thus help the ice field to grow. For all these reasons, so long as storminess remained great, the Pleistocene snowfields, according to the solar hypothesis, must have deepened and expanded. In due time, some of the snow was converted into glacial ice. When that occurred, the growth of the snowfield, as well as of the ice cap, must have been accelerated by glacial movement. Under such circumstances, as the ice crowded southward towards the source of the moisture by which it grew, the area of high pressure produced by its low temperature would expand. This would force the storm track southward in spite of the contrary tendency due to the sun. When the ice sheet had become very extensive, the track would be crowded relatively near to the northern margin of the trade wind belt. Indeed, the Pleistocene ice sheets, at the time of their maximum extension, reached almost as far south as the latitude now marking the northern limit of the trade wind belt in summer. As the storm track, with its frequent low pressure, and the subtropical belt with its high pressure were forced nearer and nearer together, the barometric gradient between the two presumably became greater, winds became stronger, and the storms more intense. This zonal crowding would be of special importance in summer, at which time it would be most pronounced. In the first place, the storms would be crowded far upon the ice cap, which would then be protected from the sun by a cover of fog and cloud more fully than at any other season. Furthermore, the close approach of the trade wind belt to the storm belt would result in a great increase in the amount of moisture drawn from the belt of evaporation which the trade winds dominate. In the trade wind belt, clear skies and high temperature make evaporation especially rapid. Indeed, in spite of the vast deserts, it is probable that more than 3/4 of the total evaporation now taking place on the earth occurs in the belt of trades, an area which includes about 1/2 of the earth's surface. The agency which could produce this increased drawing northward of moisture from the trade wind belt would be the winds blowing into the lows. According to the cyclonic hypothesis, many of these lows would be so strong that they would temporarily break down the subtropical belt of high pressure which now usually prevails between the trades and the zone of westerly winds. This belt is even now often broken by tropical cyclones. If the storms of more northerly regions temporarily destroyed the subtropical high-pressure belt, even though they still remained on its northern side, they would divert part of the trade winds. Hence the air which now is carried obliquely equatorward by those winds would be carried spirally northward into the cyclonic lows. Precipitation in the storm track on the margin of the relatively cold ice sheet would thus be much increased, for most of the winds from low latitudes carry abundant moisture. Such a diversion of moisture from low latitudes probably explains the deficiency of precipitation along the heat equator at times of solar activity, as shown in Figure 3. Taken as a whole, the summer conditions, according to the cyclonic hypothesis, would be such that increased evaporation in low latitudes would cooperate with increased storminess, cloudiness, and fog in higher latitudes to preserve and increase the accumulation of ice upon the borders of the ice sheet. The greater the storminess, the more this would be true, and the more the ice sheet would be able to hold its own against melting in summer. Such a combination of precipitation and of protection from the sun is especially important if an ice sheet is to grow. The meteorologist needs no geologic evidence that the storm track was shoved equatorward by the growth of the ice sheet, for he observes a similar shifting whenever a winter's snow cap occupies part of the normal storm tract. The geologist, however, may welcome geologic evidence that such an extreme shift of the storm track actually occurred during the Pleistocene. Harmer, in 1901, first pointed out the evidence, which was repeated with approval by Wright of the Island Geological Survey in 1914. According to these authorities, numerous boulders of a distinctive chalk were deposited by Pleistocene icebergs along the coast of Ireland. The distribution shows that at the time of maximum glaciation, the strong winds along the south coast of Ireland were from the northeast, while today they are from the southwest. Such a reversal could apparently be produced only by a southward shift of the centre of the main storm track from its present position in Northern Ireland, Scotland and Norway, to a position across northern France, central Germany, and middle Russia. This would mean that while now the centres of the lows commonly move northeastward a short distance north of southern Ireland, they formerly moved eastward a short distance south of Ireland. It will be recalled that in the northern hemisphere the winds spiral into a low counterclockwise, and that they are strongest near the centre. When the centres pass not far north of a given point, the strong winds therefore blow from the west or southwest, while when the centres pass just south of that point, the strong winds come from the east or northeast. In addition to the consequences of the crowding of the storm track toward the trade wind belt, several other conditions presumably operated to favor the growth of the ice sheet. For example, the lowering of the sea level by the removal of water to form the snowfields and glaciers interfered with warm currents. It also increased the rate of erosion, for it was equivalent to an uplift of the land. One consequence of erosion and weathering was presumably a diminution of carbon dioxide in the atmosphere, for although the ice covered perhaps a tenth of the lands and interfered with carbonation to that extent, the removal of large quantities of soil by accelerated erosion on the other 9/10 perhaps more than counterbalanced the protective effect of the ice. At the same time, the general lowering of the temperature of the ocean as well as the lands increased the ocean's capacity for carbon dioxide and thus facilitated absorption. At a temperature of 50 degrees Fahrenheit, water absorbs 32% more carbon dioxide than at 68 degrees. The high waves produced by the severe storms must have had a similar effect on a small scale. Thus, the percentage of carbon dioxide in the atmosphere was presumably diminished. Of less significance than these changes in the lands and the air, but perhaps not negligible, was the increased salinity of the ocean which accompanied the removal of water to form snow, and the increase of the dissolved mineral load of the rejuvenated streams. Increased salinity slows up the deep-sea circulation, as we shall see in a later chapter. This increases the contrast from zone to zone. At times of great solar activity, the agencies mentioned above would apparently cooperate to cause an advance of ice sheets in lower latitudes. The degree of solar activity would have much to do with the final extent of the ice sheets. Nevertheless, certain terrestrial conditions would tend to set limits beyond which the ice would not greatly advance unless the storminess were extraordinarily severe. The most obvious of these conditions is the location of oceans and of deserts or semi-arid regions. The southwestward advance of the European ice sheet and the southeastward advance of the Labradorian sheet in America were stopped by the Atlantic. The semi-aridity of the Great Plains produced by their position in the lee of the Rocky Mountains stopped the advance of the Gilbertian ice sheet from the southwest. The advance of the European ice sheet southeast seems to have been stopped for similar reasons. The cessation of the advance will be brought about in such an area not alone by the light precipitation and abundant sunshine, but by the dryness of the air, and also by the power of dust to absorb the sun's heat. Much dust would presumably be drawn in from the dry regions by passing cyclonic storms and would be scattered over the ice. The advance of the ice is also slowed up by a rugged topography, as among the Appalachians in northern Pennsylvania. Such a topography, besides opposing a physical obstruction to the movement of the ice, provides bare south-facing slopes which the sun warms effectively. Such warm slopes are unfavorable to glacial advance. The rugged topography was perhaps quite as effective as the altitude of the Appalachians in causing the conspicuous northward dent in the glacial margin in Pennsylvania. Where glaciers lie in mountain valleys, the advance beyond a certain point is often interfered with by the deployment of the ice at the mouths of the gorges. Evaporation and melting are more rapid where a glacier is broad and thin than where it is narrow and thick, as in a gorge. Again, when the topography or the location of oceans or dry areas causes the glacial lobes to be long and narrow, the elongation of the lobe is apparently checked in several ways. Toward the end of the lobe, melting and evaporation increase rapidly because the planetary westerly winds are more likely to overcome the glacial winds and sweep across a long, narrow lobe than across a broad one. As they cross the lobe, they accelerate evaporation and probably lessen cloudiness, with a consequent augmentation of melting. Moreover, although lows rarely cross a broad ice sheet, they do cross a narrow lobe. For example, Nansen records that strong lows occasionally cross the narrow southern part of the Greenland ice sheet. The longer the lobe, the more likely it is that lows will cross it, instead of following its margin. Lows which cross a lobe do not yield so much snow to the tip as do those which follow the margin. Hence elongation is retarded and finally stopped, even without a change in the Earth's general climate. Because of these various reasons, the advances of the ice during the several epochs of a glacial period might be approximately equal, even if the durations of the periods of storminess and low temperatures were different. Indeed, they might be sub-equal, even if the periods differed in intensity as well as length. Differences in the periods would apparently be manifested less in the extent of the ice than in the depth of glacial erosion and in the thickness of the terminal moraines, outwash plains, and other glacial or glacial fluvial formations. Having completed the consideration of the conditions leading to the advance of the ice, let us now consider the condition of North America at the length of maximum glaciation. Over an area of nearly 4 million square miles, occupying practically all the north half of the continent and part of the southern half, as appears in Figure 6, the surface was a monotonous and almost level plain of ice covered with snow. When viewed from a high altitude, all parts except the margins must have presented a uniformly white and sparkling appearance. Along the margins, however, except to the north, the whiteness was irregular, for the view must have included not only fresh snow, but moving clouds and dirty snow or ice. Along the borders where melting was in progress, there was presumably more or less spottedness due to morainial material or glacial debris brought to the surface by ice shearage and wastage. Along the dry southwestern border, it is also possible that there were numerous dark spots due to dust blown onto the ice by the wind. Figure 6 is displayed on the page, distribution of Pleistocene ice sheets, after Schuchert. The Great White Sheet with its rugged border was roughly circular in form, with its center in central Canada. Yet there were many departures from a perfectly circular form. Some were due to the oceans, for except in northern Alaska, the ice extended into the ocean all the way from New Jersey around by the north to Washington. On the south, topographic conditions made the margin depart from a simple arc. From New Jersey to Ohio, it swung northward. In the Mississippi Valley, it reached far south. Indeed, most of the broad wedge between the Ohio and the Missouri rivers was occupied by ice. From latitude 37 degrees near the junction of the Missouri and the Mississippi, however, the ice margin extended almost due north along the Missouri to central North Dakota. It then stretched westward to the Rockies. Farther west, lowland glaciation was abundant as far south as western Washington. In the Rockies, the Cascades, and the Sierra Nevadas, glaciation was common as far south as Colorado and southern California, respectively, and snowfields were doubtless extensive enough to make these ranges ribbons of white. Between these lofty ranges lay a great unglaciated region, but even in the Great Basin itself, in spite of its present aridity, certain ranges carried glaciers, while Great Lakes extended widely. In this vast field of snow, the glacial ice slowly crept outward, possibly at an average speed of half a foot a day, but varying from almost nothing in winter at the north to several feet a day in summer at the south. The force which caused the movement was the presence of ice piled up not far from the margins. Almost certainly, however, there was no great dome from the center in Canada outward, as some early writers assumed. Such a dome would require that the ice be many thousands of feet thick near its center. This is impossible because of the fact that ice is more voluminous than water, about 9% near the freezing point. Hence, when subjected to sufficient pressure, it changes to the liquid form. As friction and internal heat tend to keep the bottom of the glacier warm, even in cold regions, the probabilities are that only under very special conditions was a continental ice sheet much thicker than about 2,500 feet. In Antarctica, where the temperature is much lower than was probably attained in the United States, the ice sheet is nearly level. Several expeditions having travelled hundreds of miles with practically no change in altitude. In Shackleton's trip, almost to the South Pole, he encountered a general rise of 3,000 feet in 1,200 miles. Mountains, however, projected through the ice even near the pole, and the geologists conclude that the ice is not very thick, even at the world's coldest point, the South Pole. Along the margin of the ice, there were two sorts of movement, much more rapid than the slow creep of the ice. One was produced by the outward drift of snow carried by the outblowing dry winds, and the other, more important, was due to the passage of cyclonic storms. Along the border of the ice sheet, except at the north, storm presumably closely followed storm. Their movement, we judge, was relatively slow until near the southern end of the Mississippi lobe, but when this point was passed they moved much more rapidly, for then they could go toward instead of away from the far northern part, which the sun prescribes when solar activity is great. The storms brought much snow to the ice field. perhaps sometimes in favoured places as much as 100 feet a year, which is recorded for some winters in the Sierra at present. Even the unglaciated intermontane Great Basin presumably received considerable precipitation, perhaps twice as much as its present scanty supply. The rainfall was enough to support many lakes, one of which was 10 times as large as Great Salt Lake, and grass was doubtless abundant upon many slopes which are now dry and barren. The relatively high precipitation in the Great Basin was probably due primarily to the increased number of storms, but may also have been much influenced by their slow eastward movement. The lows presumably moved slowly in the general region, not only because they were retarded and turned from their normal path by the cold ice to the east, but because during the summer the area between the Sierra snowfields on the west and the Rocky Mountain and Mississippi Valley snowfields on the east was relatively warm. Hence it was normally a place of low pressure and therefore of in-blowing winds. Slow-moving lows are much more effective than fast-moving ones in drawing moisture northwestward from the Gulf of Mexico, for they give the moisture more time to move spirally first northeast under the influence of the normal southwesterly winds, then northwest and finally southwest as it approaches the storm center. In the case of the present lows, before much moisture-laden air can describe such a circuit, first eastward and then westward, the storm center has nearly always moved eastward towards the Rockies and even across the Great Plains. A result of this is a regular decrease in precipitation northward, northwestward, and westward from the Gulf of Mexico. Along the part of the glacial margins, where for more than 3,000 miles the North American ice entered the Atlantic and the Pacific Oceans, myriads of great blocks broke off and floated away as stately icebergs, to scatter boulders far over the ocean floor and to melt in warmer climes. Where the margin lay upon the lands, numerous streams issued from beneath the ice, milk white with rock flour, and built up great outwash plains and valley trains of gravel and sand. Here and there, just beyond the ice, marginal lakes of strange shapes occupied valleys which had been damaged by the advancing ice. In many of them the water level rose till it reached some low point in the divide and then overflowed, forming rapids and waterfalls. Indeed, many of the waterfalls of the eastern United States and Canada were formed in just this way, and not a few streams now occupy courses through ridges instead of parallel to them, as in pre-glacial times. In the zone to the south of the continental ice sheet, the plant and animal life of boreal, cool climate and warm temperature regions commingled curiously. Heather and Arctic willow crowded out elm and oak. Musk ox, hairy mammoth, and marmot contested with deer, chipmunk, and skunk for a chance to live. Near the ice on slopes exposed to the cold glacial gales, the immigrant boreal species were dominant, but not far away in more protected areas, the species that had formerly lived there held their own. In Europe during the last two advances of the Great Ice Sheet, the caveman also struggled with fierce animals and a fiercer climate to maintain life in an area whose habitability had long been decreasing. The next step in our history of glaciation is to outline the disappearance of the ice sheets. When a decrease in solar activity produced a corresponding decrease in storminess, several influences presumably combined to cause the disappearance of the ice. Most of their results are the reverse of those which brought on glaciation. A few special aspects, however, some of which have been discussed in Earth and Sun, ought to be brought to mind. A diminution in storminess lessens outward convection, wind velocity, and evaporation, and these changes, if they occurred, must have been united to raise the temperature of the lower air by reducing the escape of heat. Again, a decrease in the number and intensity of tropical cyclones presumably lessened the amount of moisture carried into mid-latitudes, and thus diminished the precipitation. The diminution of snowfall on the ice sheets, when storminess diminished, was probably highly important. The amount of precipitation on the sheets was presumably lessened still further by changes in the storminess of middle latitudes. When storminess diminishes, the lows follow a less definite path, as Comer's maps show, and on the average a more southerly path. Thus, instead of all the lows contributing snow to the ice sheet, a large fraction of the relatively few remaining lows would bring rain to areas south of the ice sheet. As storminess decreased, the trades and westerlies probably became steadier, and thus carried to high latitudes more warm water than when often interrupted by storms. Steadier southwesterly winds must have produced a greater movement of atmospheric as well as oceanic heat to high latitudes. The warming due to these two causes was probably the chief reason for the disappearance of the European ice sheet and of those on the Pacific coast of North America. The two greater American ice sheets, however, and the glaciers elsewhere in the lee of high mountain ranges probably disappeared chiefly because of lessened precipitation. If there were no cyclonic storms to draw moisture northward from the Gulf of Mexico, most of North America east of the Rocky Mountain barrier would be arid. Therefore, a diminution of storminess would be practically effective in causing the disappearance of ice sheets in these regions. That evaporation was an especially important factor in causing the ice from the Keewatin center to disappear is suggested by the relatively small amount of water-sorted material in its drift. In South Dakota, for example, less than 10% of the drift is stratified. On the other hand, Salisbury estimates that perhaps a third of the Labradorian drift in eastern Wisconsin is crudely stratified, about half of that in New Jersey, and more than half of the drift in Western Europe. When the sun's activity began to diminish, all these conditions, as well as several others, would cooperate to cause the ice sheets to disappear. Step by step with their disappearance, the amelioration of the climate would progress so long as a period of solar inactivity continued and storms were rare. If the inactivity continued long enough, it would result in a fairly mild climate of high latitudes, though so long as the continents were emergent, this mildness would not be of the extreme type. The inauguration of another cycle of increased disturbance of the sun, with a marked increase in storminess, would inaugurate another glacial epoch. Thus a succession of glacial and interglacial epochs might continue so long as the sun was repeatedly disturbed. End of section 7.